All right, so next, after looking at gravitational fields, you guys are going to start looking at electric fields, which you guys started in grade 11. In fact, you guys did a whole bunch of stuff with electric fields in grade 11, more than gravity and more than magnetic, lots of stuff with electric fields. So we'll be reviewing that type of stuff first. And the great thing is when we get to the fancier, schmancier type electric fields, a lot of it is very, very, very similar to the gravitational stuff you guys have done. So if you can do it with gravity, it sure makes it a lot easier to do with the electric stuff. So let's review some of the stuff that you guys did last year in electric fields. So for example, what you guys took last year is a course that comes from charge, which is a combination of electrons and protons, and you guys drew electric fields, and standard color coding is red, and you guys would draw them going out from positives, and you guys drew them going into negatives. Even though we know the field actually radiates out from both of them, we draw them based on their interactions with a positive test charge, or basically a proton. So if you put a proton here, it would be repelled by the positive, so we draw the field lines going out. And if you put a proton here, it would go towards it, so we draw the field lines going in. And then you guys also did stuff like this last year, where you'd have two charges, and you guys would draw the electric fields in between them, something like this. All right, you guys drew electric field diagrams, stuff like that. You guys also drew ones for parallel plates is really, really common for what you guys did last year. Stuff like this. And you guys would have like a positive plate, and you guys have a negative plate. And then we would draw the fields, something like this. And those are really good for nice, uniform, strong electric fields, and great for calculating forces on subatomics and that type of stuff. So you guys did a lot of stuff with that last year. So that's what we'll review again today, is some little bit of stuff like this, and as well as, you guys had the formula last year that electric force was equal to QE. That's the basic formula that you guys used last year, mostly in parallel plate setups like this, where the forces are nice and uniform. So look at that type of stuff as well, and just sort of practice some of the basic ideas of what you guys did last year, and then we'll get a little more detail about electric fields a little bit later on and stuff like that. But we'll just start with some basics from good old grade 11. For example, start with some simple stuff. You guys had electric fields. You have electric field like this. There we go. There's an electric field. And let's just take something really simple. We'll take a proton, and let's say the field is 6,500 newtons per coulomb. And what you guys would do last year is you guys would do stuff like this, like find the force on the proton. You guys would use F equals QE. Of course, the charge of protons, the 1.6 negative 19, that's in that super sheet that you guys have, that inside cover of your textbook. Make sure you know that number, because you'll be using it quite a bit. So you guys can calculate the force on the proton, no problem. You guys did this quite a bit last year. So we've got the charge of the proton, which of course is a constant, and we multiply that by the electric field of 6,500 newtons per coulomb, and we get a force of about 1.04 times 10 to the negative 15 newtons, which doesn't seem like a lot, except since the mass is so small for a proton, when you guys would extend this and do stuff like finding the acceleration, and you guys do force divided by mass, you take that force of, really, really small value, 1.04 negative 15, and you divide that by the mass of the proton, which is 1.67 to the negative 27, you get an acceleration of around 6.3 times 10 to the 11 meters per second squared. So really, really massive accelerations. That's one of the things we had last year, is huge accelerations for these charges, even though the forces are really, really small. And of course, this guy right here, the proton, would go with the field, because that's the way fields are drawn. And if you had a parallel plate, there would be a negative plate on the left, and there would be, a positive plate on the left, a negative plate on the right, and it would be attracted to the negative plate. Now you can do the same type of thing for electrons. So you guys did the same thing for electrons last year. Force-wise would be the exact same thing, because the charge is the same. You'd have the exact same force except, of course, the biggest difference is the direction, because the proton is going to the right, the electron would go to the left. So often this is called a negative force, but the negative just means it's going against the field. It doesn't necessarily mean what direction it is, so I prefer to use arrows. We did that a lot in grade 11. But the same charge, same field, they're going to experience the exact same force. The biggest difference, of course, kicks in when you calculate that acceleration. The mass of an electron is considerably smaller than that of a proton, just over 1,800 times less. So when you calculate it, it's going to have a much higher acceleration. I'm just going to round off here a little bit, like it's like around 1.1, 1.2 times 10 to the 15 meters per second squared. So these are like the basic types of calculations you guys did last year. So we're just going to practice that a little bit because this type of stuff never really goes away. And then we'll get into the grade 12 stuff later on. Okay, so let's get rid of this stuff and practice some of the types of things you guys did last year and work with that. Okay, so let's take something else. Let's, get a couple parallel plates here. It's wrong color. That's better. Okay, we'll get another one. So this type of stuff you guys did last year a lot. All right, there we go. And let's say we've just got, say this is the positive plate, negative plate. So then with this, the electric field would be going in this direction. And then let's say we've got a proton. The proton, of course, is going to go flying across. And let's say, you guys did a lot of prefixes as well. So let's say these two plates are 72 micrometers apart, and it took 0.14 nanoseconds to get across. And what we're going to do is we're going to find the electric field. So in grade 11, which you commonly would have done, since you have the distance and you have the time, you guys would have typically found the average V using distance and time. You would have then doubled that in order to get the change in V. And then what you would have done is you would have found the acceleration using change in V over change in T. And then that leads to forces, etc., etc., etc. But now with the grade 12 expressions that you have, you guys can do this a little bit quicker, a little more efficiently. So you can do it this way if you really want to. It doesn't make any difference. But using the distance equals 1/2 AT squared expression works really, really nicely to find that acceleration a little bit quicker with less error, less rounding, etc. So if we use the 1/2 AT squared, we can find the acceleration of that proton a little bit quicker. Okay, so that would give us around 7.3435 times 10 to the 15 meters per second squared. All right, well, now we got our acceleration. We can find our force, and this would be our net force, which of course is equal to ma. And of course, since it's an electric field, this is going to be equal to QE. So again, this is exactly what you guys did in grade 11. So if we want to find the E would then be the force, the ma, divided by the Q. And of course, the mass of a proton, that one, it's in your list. Acceleration you have, you just found that. Charged proton, same as always. And then you can find the electric field. And this should give us around 7.7 times 10 to the 7 newtons per coulomb. And there's our electric field. Okay, so aside from using the 1/2 AT squared expression, this is straight from grade 11, good old-fashioned grade 11 review. Okay, well, let's do something similar to this. I'm just going to take this and just copy and paste it because it's easier. There we go, bring that over there. Except we're going to switch this out. We're not going to use a proton this time. Okay, so this time we are going to use an alpha particle. So here's our alpha particle, and if you remember what an alpha particle is actually a helium nucleus, so a really common form of radiation, and it is going to go across the field or between the two plates. And let's say when it gets to this side, over here, when it's going this side, let's say it's going 0.18c. So remember, it's often common to relate how fast these things are going to the speed of light. And we'll say this thing is going 0.18c when it gets to the other side. So of course, going really, really, really fast. And let's say it took, I'll make something up here. Let's say it took 6.4 nanoseconds for it to get across. Okay, so we got this and this, so we can find a few things with that. And let's see if we can find the electric field. Okay, actually we just found the electric field. Let's try something else here. Let's see if we can find, well, no, that's okay. Let's just find the electric field. May as well, no big deal. All right, so what's the electric field again? So we can do something really, really similar. The information is a little bit different, so no big deal. And we'll be able to incorporate some of the other stuff that you guys have done with your 12 kinematics into this. Okay, so first things first, we need the charge and mass of the helium nucleus. So if you remember, we need to find out the charge of the nucleus and the mass of the nucleus. And often when I do this, I use a capital Q for my charge of my nuclei. Big Q, little q doesn't really make that much difference. So if you remember, for charge, helium nucleus has 2 protons in it, and the mass has got 4 things. It's going to multiply the mass of protons and neutrons, going to do that times 4, using 4 times the AMU, and then 2 times the charge of an electron or proton, in this case proton because it's nucleus, and you have the charge. So the charge will be about 3.2 times 10 to the negative 19 coulombs. We've done that quite a bit last year. Okay, and then of course for the mass, you should get about 6.68 times 10 to the negative 27 kilograms. So 2 times the charge of a proton, 4 times the atomic mass unit, and you'll have somewhere around there. Okay, so remember, being able to try and charge a mass nuclei is going to be really important for this type of stuff. Okay, all right. Also, we're going to convert this, hitting going 0.18c. So I do 0.18 times the speed of light, and this thing is going about 0.54 times 10 to the 8 meters per second. So I need to convert that into actual meters per second so I can use it. Okay, so now it's going to be very similar to what we had before. I've got time, I've got v, so I can find some acceleration stuff. So I can find my acceleration with this. Of course, acceleration, that is not only my final v, but that'll be my change in v, and I have my time. So if I divide those two out, I can get my acceleration, which is about 8.44 times 10 to the 15 meters per second squared. Okay, well, I got my acceleration, and now the rest is pretty much the exact same thing as before. The electric field would be ma divided by q. I found my mass, I found my charge, and I just calculated my acceleration, and I can put those together to get my electric field. And hopefully that gives us approximately 1.76 times 10 to the 8 newtons per coulomb for an electric field for that one. Okay, so this one is basically, VAT. We use the good old classic VAT. The classics never go away. Remember how to find charge and mass of a nucleus. We're using speed of light references for speeds and converting those into actual speeds. These are all basic skills that we've worked on in grade 11. Okay, so we just got to review some of the stuff. Some of the stuff never really goes away, so it's good practice. Make sure you do a little practice on your own as well. Review some stuff. You can even go back and find your grade 11 stuff. It can come in really handy because it's a great place to start.